problem, what is entering temperature? This is a visual, this is the problem visually, stating essentially the same things, what we have and what we're looking for.
So after reading the problem and looking at the flow chart, we have to find out what is given to us and what we really need to solve for and what calculation of data is required to basically come up with that ultimate answer. They've given us heat loss, so we automatically know that's a negative sign for Q, negative 120.2 kilojoules per kilomole of CO. Our final temperature is 800 Kelvin, pressure is constant at 1 atm, and we're solving for initial temperature. A couple of things we need to look at in detail, which is our reaction. We know there's 1-to-1 ratios to chemistry and it's already balanced. Other thing that is pointed out there is 100% excess of water is actually double sized in stoichiometry, so we know that already there that we have 2 moles of H2O as a feed. Q is again negative for this value, 120.2 kilojoules per kilomole of CO, and we just need to solve for our initial temperature based on our final temperature at 800 Kelvin.
Theory and basic equation. So those are some formulas we use to solve for the heat of reaction method and heat of formation method. The first one is fractional excess, which is the ratio of the excess to the stoichiometric requirement. Use this to get the number of moles of H2O entering the reactor. And then we have extent of reaction, which we use to get the number of moles for our products. And Hess law, we use this to get our variable, the T, for our heat of reaction method. And then we have the change of specific enthalpy at constant P, which is the integral of Cp from T1 to T2. And first law of thermodynamics, we use this for the energy balance. And then we have heat of reaction method, standard heat of reaction method. It can be solved with two methods, heat of formation method and heat of combustion method. It's the same, but in heat of combustion is just one that combustion reacting products.
We have also 2 equations here were used. The first one is the change in enthalpy is equal to the sum of the number of moles multiplied the specific enthalpy out minus the sum of the number of the moles multiplied by the specific enthalpy in. And the second one is the change of the specific enthalpy is equal to the heat of formation plus the integration of Cp when T changes from T1 to T2. There was some sources were used. The first one was B1, table B1, which the selected physical properties data, and table B2, the heat capacities, and table B8, specific enthalpies of selected gases in SI units. There were some assumptions were made. The first one is not adiabatic, which means heat is transferred from the system. Assume a basis of 1 mole CO feed with 100% excess water vapor in the feed. The reaction is performed at 1 atmosphere and remains constant. Combustion goes to completion. The change in potential energy, kinetic energy, and shaft work are assumed to be 0 because there is no high change, system movement, or shaft work involved. The energy balance equation reduced to heat equal to the change of enthalpy. The reactant CO is a gas mixed in with water vapor initially, and this is proven after solving for the inlet temperature.
Okay, so next we have our heat of reaction solution strategy. The first step in order to solve our heat of reaction method is to complete any material balances that balance calculations that might be needed. Next would be to choose a reference state to solve for any change in enthalpies and change in specific enthalpy calculations that we may need to fill in. Next, draw a table and fill in all molar values and specific enthalpies and solve for any unknown values that are left to fill in. Next would be to calculate the this case, in our problem statement, we are not given the heat of reaction, so we have to solve for it. Last step would be to solve for the overall change in enthalpy and insert it into our energy balance equation to solve for any unknown variables. In this case, we're solving for our initial temperature. So our first step would be, like always, like in any problem, is to draw a flow chart. In this case, it's just what is given in our problem statement. We chose a basis of 1 mole of carbon monoxide and went from there.
Okay, so then we did the material balances using the extended reaction approach, and we calculated through our basic calculations to get the number of moles. So why do we need the number of moles, you ask? So that way we can fill them into this enthalpy table. So this enthalpy table, the key thing to note is our references are CO gas, H2O, H2, and CO2 at 25 degrees Celsius and 1 ATM. And we filled in once again the moles that we calculated previously, and then we put H1, H2, H3, we're going to calculate those again.
So here we have the B2 table that we use to calculate our heat capacity. Here's our components, any species highlighted. And this table is we used for our final specific heat to calculate our final heat specific heat enthalpy. We're using those numbers since we don't have the exact 526 degrees Celsius given on the table, so we just use this number and interpolate to get our given temperature specific heat enthalpy. And here's the expression highlighted. That's what we use to calculate our C.
Okay, so no matter what way you do with this, you're going to have to solve for these contributions to your change in enthalpy to change in temperature. And by now you've seen all these different integrals we have. And you'll see the unknown pops up in the first 2 integrals. The upper limit integrations are unknown TI. And you'll integrate all of these. And for 2 of them, you'll get some 4th-order polynomials with the unknown being the temperature. And the other 3 you'll be able to solve for explicitly. And we'll later use those for our energy balance to solve for T. Once again, as a side note, if you can find a chart with the right references, you can actually skip some of these steps if you can do inducible linear interpolation. We actually found one and showed the numbers here, but they're not as accurate because they follow linear interpolation as opposed to a 4th-order polynomial. But they did be pretty accurate because if you look at those terms of the heat capacity, the first one's a lot larger than all the other ones. So they're still pretty good.
There's 2 ways to calculate the standard heat of reaction. You can do heat of combustion or heat of formation. All these are taken from table B1. The main differences being if you use heat of combustion, you have to do reactants minus products, but you also have to factor in 44.01, which is the heat of vaporization of water. Here's the energy balance equation. Basically, we have no shaft work, no kinetic energy, and no potential energy, so the equation becomes Q equals the change in temperature.
We plug in our numbers that we just calculated. The equation is Q equals delta H, which is extended reaction times standard heat reaction, plus moles times specific enthalpy out, minus moles times specific enthalpy in. We plug in our numbers and we come up with a temperature of 172 degrees centigrade or 445 Kelvin. Now the heat of formation solution strategy, we first complete our material balances to the extent that we can. Then we choose our reference states for specific enthalpy, and they basically help us in preparing the inlet-outlet table. Then we calculate each component's enthalpies, whatever we can, and if we cannot, we come up with the equation in the form of T. And then we put out overall change in enthalpy, and we solve for our unknown variable, which is our initial temperature.
So basically, again, we start doing our flow chart, and this is our equation. We took a basis of 1 mole of carbon monoxide, and we have a initial temperature unknown. We have our unknown moles, but we know that we have 100% assessed water, and then we know our temperature out and our heat transfer. The second step is doing the material balance. Here we did standard reaction, but it can also be done as atomic balance because in formation we do not use the standard reaction in the problem, so you can do it as atomic balance as well. So, and you do material balance with the standard reaction here.
Now, so for this table, it's similar to before, except we use different reference now. As you see, we have the carbon right on top. We still use the same temperature of 25 Celsius and 1 atm for pressure. For this calculation part, it's also similar, except as you see here, we use the specific heat of formation plus the integration part. For example, for H4, the answer we got is negative 378.
This slide should look pretty similar to you. I'm just going to reiterate what was said earlier. For the H3, H4, and H5s, because they can't be solved explicitly, there's no variables, you can linearly interpolate. For H1 and H2, which is where the T was, the inlet temperature we're trying to find, you can't use this method because obviously the variable's there. It's faster, it's less accurate. We don't necessarily condone it if you're looking for the most accurate answer, but it can be done, and also it can be used to double check your answer, see if it's the same homework. And same thing here, you have the general material balance. There's no change in height, no moving parts, no shaft work, so everything just boils down to Q